Okay, here is part 3. I got cut off there by the bell in part 2, but we have the situation where we have a cup of water that has a mass of 500 grams, which is half a kilogram, and we're trying to heat it up from room temperature to boiling, meaning 100 degrees Celsius, and how much heat energy is required. So we are using our formula Q equals mc delta T, where Q is our variable, our heat energy that we're trying to find, and we have half a kilogram, so the mass of water being heated up is half a kilogram. The specific heat of water we said was 4, sometimes you'll see 4180, sometimes more specifically you'll see 4187. So let's leave it at that. And then the change in temperature, if it's going from 25 up to 100, do you see how it has to increase by 75 degrees Celsius? And again, 75 degrees Celsius is the same as 75 degrees Kelvin if we're talking about a change in temperature, because one degree Kelvin is the same as 1 degree Celsius. They're just shifted by a certain amount. So after we multiply, let's see, calculator says 0.5 times 4180 times 75. So it looks like we have, our calculator is telling us this number, and that's a lot of significant figures based on our original information, so maybe we would just say something like 1.57 times 10 to the 1, 2, 3, 4, 5 joules. So frequently, big numbers you'll see measured in kilojoules, which is 1,000 joules. So this would be something like 1.57 times 10 to the 2 kilojoules. Okay. Last type of question looks like, let's say the room temp cup of water, 25 degrees Celsius, 500 grams, so it's the same situation, is heated up a bit by placing a hot, so 100 degrees Celsius piece of aluminum. What is the final equilibrium temperature? So I can't go back, so I need to look up what the aluminum specific heat is. Specific heat aluminium. So if we're going to draw a diagram, it looks like this. We have water. We have some aluminum. So this is the aluminum. It is at 100 degrees Celsius. And the water is at 25 degrees Celsius. And we have 200 grams of aluminum, and we have 500 grams of water. So specific heat of aluminum, 908. We had 8 something. This says 900. Great. This is not, okay, interesting that they're that different. I think on the previous page, it said that the specific heat of aluminum was 873, let's say. So here's what happens is when the hot piece of aluminum is put into the water, when the hot piece of aluminum is put into the water, it's going to lose heat and the water is going to gain heat. So we can say something like this: the heat lost by aluminum equals the heat gained by the water. So obviously the temperature of the aluminum is going to go down and the temperature of the water is going to go up. So it's tempting to be like, oh, let's just average them, and the average of 25 and 100 would be whatever it is. But that's not the way it works, and that's not the way it works for two reasons. One is there are different amounts. There's more water than there is aluminum. And the other reason is that aluminum is easier to heat up and cool down than water is. So the change in temperature is going to be greater for the aluminum than for the water for those two reasons. But based on this, we can say Q, so the heat lost by the aluminum, equals the heat gained by the water. And if we're using our Q equals mc delta T, we could say mc delta T for the aluminum equals mc delta T for the water. And for our aluminum, our mass is 0.1. So 100 grams is 0.1 kilograms. Specific heat of aluminum, and let's pretend that the previous page I told you 873, that's right from your textbook, but I could be wrong. But if I go back in this video, then it cancels it all out, so I'm not going to do it. Now, for the change in temperature, we know that aluminum went from 100 down to the equilibrium temperature. So what is the final equilibrium temperature? This is what we're solving for. We don't know what it is, but we know that, let's say it's 80 degrees. It definitely won't be. It's going to be more like 30 or something. But if it were 80 degrees, we know that the temperature of the aluminum went down by 20 degrees. For the water, so this is our right-hand side of the equation, heat gained by water, so the mass of the water was 500 grams, and that was our 0.5 kilograms. Specific heat of water, we were using 4180. And then for the temperature, we know that the temperature of water is going to go up. So let's say it went up to 30. We would do 30 minus 25 to get the change in temperature. So it's going to be T minus 25, like so. So what we've said here is that mass times specific heat times change in temperature equals mass times specific heat times change in temperature, because the heat energy lost by the aluminum equals the heat energy gained by the water. So once we have that equation, again, we're solving for T. This is the equilibrium temperature, what these two will sort of end up at, and we're assuming that this is perfectly insulated. But let's see. When we multiply, so this becomes 87.3, 100 minus T, and half of 4180. We have 2090. We're going to distribute. And distribute 2090 times 25. Alright, and then it's looking like, okay, we learned that in algebra where we're going to get the t's on the same side. So I'm going to add this over here, and then move the number over here, and then we'll divide as the last step. So adding this to both sides, plus 8730, gives us 60980 equals, and then adding this many t's over to this side gives us 2090 plus 87.3. And last step will be to divide both sides by 2177.3. So this is showing 28.0, and so that would be degrees Celsius. So notice how close that was to 25, right? The water didn't heat up that much, but the aluminum definitely cooled down a bunch. But the change in thermal energy for both was the same.